have sort of make videos that I put up on Susie Q on YouTube. So today we're gonna use my phone and hope to God that it works out. Okay.
We can use this one also, of course.
All right, and this makes it go forward. Oh,
forward, and then here use a pointer.
Okay. Oh, okay. Oh, I like lasers. It has something to do with my talk. Oh, I'll sit down. Not that there's a big difference, mind you. So, thanks for coming to a talk where there are two papers about Q and quantum. I'm going to talk about complementarity in physics, Q, and in mixed methods. It ends up that complementarity is something that we talk about a lot in physics, especially in relation to quantum mechanics. And of course, Stephenson talked about complementarity in his analogies between Q and physics. And then it ends up that there's also discussion about complementarity in mixed methods, which I didn't really know until I have two book chapters that are in process. And one of them is about integrating qualitative and quantitative. And basically, in my book chapter, I talk about complementarity, and the mixed method editors came back and said, you should talk about complementarity in mixed methods. And I said, well, then I will. So basically, that's the focus of the presentation, comparing and contrasting complementarity in three different kind of dimensions. Yet there's great similarity between complementarity in physics, in Q, and in mixed methods. This is the abstract, and I will not read it to you, and you are grateful. So first, let's talk about quantum mechanics. So this is a quote from Niels Bohr, who was a Danish physicist. He was a great contributor to understanding atomic structure and quantum theory. He's a Nobel Prize-winning physicist, happened to win it in 1922, and he was the person who originated using the term complementarity in physics. And so this quote that I selected is, quantum mechanics has led to a complete revision of our conception of the nature of matter and much more. And in many ways, this is what Q did for research. So a little bit about complementarity in physics. There's a number of different ways at looking at complementarity in the subatomic kind of areas in physics. This does not apply in classical physics. And the easiest one probably to describe is the one related to light, because we're all familiar with light. In fact, ancient, well, not that ancient, physicists had all kinds of conceptions trying to figure out how light worked. You might have learned about the idea that there was an ether and that helped light, right, propagate through some medium which doesn't actually exist, because we've been fascinated by light for a long time, especially scientists. The thing about light is that there are two contrasting theories. And I'll take each of these, but basically, is it a wave? Is it a particle? Is it a particle that acts like a wave? Or is it a wave that acts like a particle? This is just a really cool picture from relatively recently about, it's considered a photograph of light acting as both a particle and wave. Don't ask me any information of how they actually took that picture. I just thought it was cool. So let's start off with the wave theory in our wave-particle duality, which is all what complementarity really is. So the wave theory is necessary to explain interference and diffraction. So Young, in 1801, did his famous double-slit experiment. You may have done a double-slit experiment in high school or college physics, probably used diffraction gratings. You didn't do what he did, which was to meticulously cut slits and use candles with filters. Physics was a lot more fun in the 1800s. It is also why thin films work. So if we look, oh, I got to figure out the button, there we go. So if we have two slits, right, the particle theory says that we'll just have light go through these slits and we'll just have light. Right? Wave theory said the light waves will interfere and we'll have fringes of light and dark, right? Or if we don't have a single color, monochromatic light, then we'll see different colors, right? This is what's observed. So we know that light acts like a wave. But then there's a problem. because quantum mechanics was born, Maxwell Planck, as well as Einstein, looked at basically what we call the particle theory of light, which is the photoelectric effect. We can't explain the photoelectric effect using waves. It's impossible. The only way we can explain the photoelectric effect is to say light is a particle, photons or quanta. And we see all kinds of applications in our everyday life related to the photoelectric effect. Digital movies use this idea, digital cameras, night vision devices. Oops, wrong one. Here's my cool night vision, right? Uses Wien's displacement law, which is another way of looking at light as a particle that has energy. I won't bore you with all the exciting physics that goes with that. But the key thing is that we have two conflicting ideas about light. In certain situations, the only way we can explain the behavior is that it's a wave. And in other situations, the only way we can explain light's behavior is to say that it's a particle. And that is the duality. We have two conflicting ideas, yet we need to have both of those ideas to explain the actual complete behavior. Right? In physics, complementarity does not mean they're in conflict. They may have been in conflict at one time, but we accept that there's this duality. In quantum mechanics, right, we can extend this idea and say that, yes, in fact, right, Heisenberg said that we talk about probability functions in quantum mechanics, and it's another kind of duality where we combine objective and subjective elements. So let's talk a little bit about probability functions in quantum mechanics, because everybody always, good pre-lunch discussion, right? So basically, right, epistemologically, the conception of quantum states is the idea that quantum states are not descriptions of the properties of a quantum system, but rather reflect the state assigning observers epistemic relations to these systems. In other words, states assigned by different observers may differ as the nature and amount of knowledge may differ. Gee, that sounds just like Q methodology. Imagine that. We can also relate this idea to quantum Bayesianism, commonly referred to as cubism. I had to address cubism and Q in my book chapter, which is edited by Tony Anamakabuzi and John Hitchcock, who are I'll call them bigwigs in the land of mixed methods research, primarily in education. And so here we see that the interpretation of quantum mechanics, right, takes an agent's action and experiences as the central concerns of its theory. Of course, we all know that William Stephenson had a PhD in physics and a PhD in psychology, and he created Q. Right? And so we can see, again, these connections between quantum mechanics and Q. This is just fun. A long time ago, one of my students actually had this in some book he got, and he printed it out and he gave it to me, and I thought that makes a lot of sense to put in here. Right? So be a quantum mechanic. In a way, when we tell people that we would like them to take on Q methodology, we're kind of asking them to be a Q, right, or a quantum mechanic. So a little bit about Stephenson, quantum mechanics, and Q. We, of course, know that he drew on his knowledge of quantum mechanics in many, many manuscripts, both published and unpublished. In the study of behavior, he described the Q-sort process as a measurement tool that might influence the sorter, which is analogous to quantum mechanics, where we know that attempting to measure the position of a particle in a well makes the particle move. Very much like Q-sorts. Even yesterday, a presenter was talking about how many of her subjects, when they did the Q-sort, commented that it made them really reflect more so on their thoughts about the topic at hand. And I think that a lot of us can describe, right, the kinds of things that people have told us after a Q-sort or written, depending on what our situation is, where they've had some kind of epiphany. Or as I describe it, I have often sat in my office and cried while I read people's, right, coming to terms with something that, right, they didn't realize about themselves. He also called Q factors as representations of likelihood. They are not certainties. Again, this is that quantum versus classical physics. And in a number of publications, Stephenson also explained that although Q factors that emerge from the analyses are implicit and operate, each Q sort provides a probability distribution that is just like a quantum state, right? So it's not set in stone. Right? I can measure the length of, right, every person in this room, their arm, their legs, just like Steve Brown did for his I always call him the alien man, right? Then we know what the R factor analysis result is. And we could take any group of people and do those measurements and come up with a regular man, and then we could sort those body parts. And we might end up with different views of what the most important body parts are. So we could have different little alien men running around. So the key idea is that subjectivity is indeterminate, and that parallels the indeterminacy of quantum theory. Right? And so we really have no way of predicting. We could guess, but we don't really know how many factors will emerge or what the factor array structure will be like until we actually do our experiments. The emergence of multiple divergent viewpoints represents a type of complementarity. That was from Stephenson. Right? He also explained that complementarity within Q offers a means of quantum theoretical explorations of thought, offering a new epistemology, just like Bohr talked about epistemology within the context of quantum mechanics. So let's talk a little bit about mixed methods in complementarity. So back in 1989, Green, Caroselli, and Graham described complementarity in mixed methods, that it enhances the interpretability with any mixed study by simultaneously implementing qualitative and quantitative methods in ways that are actually interactive, right? Back in especially the 80s and 90s in mixed methods, there were something called the paradigm wars even beforehand, which was this kind of qualitative, quantitative, I'm better than you are tug of war. Right? And this became especially intriguing when we talk more about methodologies instead of methods. So why is it mixed methods and not mixed methodologies? That's a topic that's very prominent right now in the mixed methods community, because the idea is, can we really, right, blend qualitative and quantitative processes, analyses, data collection, or is it bigger than that? Can we combine different philosophies, right? And so they have their own faulty assumptions, right? And their own arguments, right? About what mixed methods is. Just like we have our own arguments about how to extract and rotate factors. Same difference. So when we talk about Q in mixed methods, right? We can go back to 2004 when Paul Stenner and Rex Stanton Rogers wrote about Q and just used this new term because they couldn't find a term they thought was fitting for Q, and they called it qualiquantology, which is a real mouthful, and I've had to practice a number of years to be able to say that out loud. Right? I wrote my first book chapter with my advisor, Isidore Newman, back in 2010. It's a collection of articles related to mixed methods, and in a volume edited by Tedley and Tashikori. I now have 2 different book chapters in process. One is addressing Q as inherently mixed, in that it's hard to draw a distinction between what parts are quantitative and which parts are qualitative. Some here might say, well, factor analysis is always quantitative. But is it really? Even in our methodology, there are qualitative aspects. When you interpret the R factor structure, you're still doing something that's much more qualitative. And of course, I recently had a publication about how Q methodologists hold different divergent views, and I thank anybody who was here who participated in that study. And so we see, right, qualitative and quantitative in Q. We see that it can be mixed in a number of ways, and then Stenner and Stanton Rogers in 2004 also pointed out that intertwining qualitative and quantitative research methods is often unsettling for researchers. Very much like in quantum mechanics, right? The idea of, right, only being able to measure, right, momentum or, right, position, but not both, or velocity, but not multiple things like in classical physics, was very unsettling, even for people like Einstein, whose famous quote was, "God doesn't play dice." So here's a question. This is Joey Chestnut. If you don't know about competitive eating, Joey Chestnut is the world champion hot dog eater every 4th of July. There is a competition in New Jersey where basically people stuff hot dogs and hot dog buns in their mouths until, you know, the timer goes. And I believe that this year in 10 minutes, he did not beat his record. I think it was 76. It's a lot of hot dogs. But not going off on too much on Joey Chestnut, he recently stated, right, a hot dog is not a sandwich. It is something unique. And this is something that I've heard Q methodologists say as well, right? Q isn't like qualitative, it's not quantitative, it's not mixed, it's its own thing. So is Q like a hot dog? Is Q like light? Is Q like something else? So in conclusion, right, we see dualities or complementarity, right, in Q, mixed methods, and quantum mechanics. Yet they're competing theories, right, but they're not in conflict. And we need both aspects to describe what's physically happening, right? And we know that this can be unsettling, right? Whether it's quantum mechanics or in Q, a lot of times when we get feedback from, right, article reviewers from journals, they make all kinds of comments from a quantitative perspective, or sometimes a qualitative, but almost always a quantitative perspective. We don't have enough people. How do we know this? How do we know that? Right? Can you make this article also an introduction to Q? Like every article we ever write for a journal has to also be an introduction to Q. Right? In fact, right, physical science, chemistry and physics, right, is often mixed. And I think that a lot of times when people talk about scientific research, right, they think of it as purely quantitative. Even in physics, that it's purely quantitative. And that's simply not true. Right? It's a misconception about how science works. And in science, we always have qualitative and quantitative. And there is a good reason why Stephenson often discussed analogies between Q methodology and quantum mechanics, and one of the biggest takeaways, I think, is that we have complementarity, but that doesn't mean that those aspects, whether we think of them as qualitative and quantitative, or any other combination of some of the unique aspects of Q, they're not in conflict, right? They coexist in a coherent form that makes sense, hopefully, to at least Q methodologists, and maybe one day the world. Just a sample of references. It was much longer, but you would never be able to read it. I also have up here my website where I have some articles posted, and of course my YouTube channel and my ORCID ID. And that's it.
Thank you very much. Any questions, comments?
Sergio from UCL, it's more of a comment really to say that I work in building physics and the examination of how people interact with buildings at UCL, and this idea of quantitative versus qualitative completely falls apart in that you have to have both. So in my study I'm going to be doing physical measurement of the environment that people live in at the same time as actually doing this qualitative interviews within that Q sorting to understand how they perceive their environment. And without one of those, you can't really understand what's going on. So, yeah, just to endorse this idea of complementarity.
Yeah, you definitely have a complementary situation going on. A couple of slides. Tell me when. This one?
Yes. You say that the last item there's good reason why Stephenson often discussed analogies.
Mm-hmm.
I think Stephenson never discussed analogies, and he explicitly said that Q and quantum was not analogical.
Okay.
How would you respond to that?
Are you saying that, so he wasn't using quantum to describe it, but he used quantum as the basis for Q methodology in a more theoretical framework way than a way of explanation?
I'm not sure.
Oh.
I know that he explicitly said that it was not an analogy.
Okay.
Yeah. You might be.
All right. Okay. Thank you.
He said, perhaps clarify a bit, that there were striking parallels between the two, but not that Q was an analogy or could be, referred to analogically, like quantum theory. That he owed Q methodology owed nothing, he said, to quantum theory. It owed everything to the London School of Fact Analysis experiment.
Thanks, Stephen Jackson from University of Birmingham. That's just a short question, really. What do you think the benefit of coming up with a label to define or that categorises Q methodology would be? And I suppose my immediate thought is how you communicate methodology to the wider world. And I know that in previous presentations you talked about Q as a mixed method. It sounds as if you've moved a position towards saying maybe we shouldn't try to label it at all.
Oh, I wouldn't say that. I would say that there are some who object to that idea. When I did the views of factor extraction and rotation, almost everybody who participated, I had a brief questionnaire beforehand, and almost everybody said that they thought it was a mixed method. So I let them choose, was it qualitative, was it quantitative, was it a mixed method, or was it something totally unique, like none of these? And the majority of people said it's a mixed method. I think it helps us explain things in terms that researchers typically understand. I've also found that it helps me eliminate the you don't have enough subjects sorting and some of the quantitative things. I'm much more likely to get a reviewer who's a mixed methodologist. If I usually give them names of Q methodologists, but we don't have Q reviewers